Welcome. We all have those little hunches, those fleeting thoughts every day. But have you ever wondered how one of those sparks of curiosity actually becomes, well, a proven scientific fact? Today, we're going to open up the researcher's playbook and follow that exact journey from start to finish.
So, how does that happen? How do we go from a simple hunch to a fact we can actually build on? Well, the whole process, that whole journey, it really all starts with one single crucial first move. Okay, so here it is, the first move in the playbook. And you could argue it's the most important one. It's all about forming what we call an educated guess. And look, this is not just some random shot in the dark. This is the foundation for absolutely everything that comes next.
Right, so what exactly is a hypothesis? Well, the easiest way to think about it is as a really smart, reasonable suggestion about how two things might be connected. It's not plucked out of thin air. It's a statement that comes from a theory, or maybe from past experience, or even just from paying really close attention to the world. And its job? It gives the entire research project a crystal clear direction.
But here's the thing, not just any old guess will work. A really strong, useful hypothesis has to follow a few key rules. First, and this is a big one, it has to be testable. I mean, you've got to have some way to actually check if it's right or wrong, right? Second, it needs to be what we call positive. That means it states what you think is happening, not what you think ought to be happening. And finally, it has to be simple and super clear. No jargon, no confusion. Everyone should know exactly what you're proposing. All right, so you've got your solid, testable hypothesis. What's next? Well, now you've got to figure out how you're going to test it. This is all about choosing the right tools for the job. And when it comes to research, there are basically two main toolkits. You've got qualitative research, which is all about exploring ideas and the why behind things. Think interviews, observations, that kind of stuff. Then you have quantitative research. This is the one we're really going to focus on today. It's all about testing theories using measurements and cold, hard numbers. This is the path you take when you want to test a hypothesis with data. So when you step into that quantitative world, you're dealing with things called variables. The first one you need to know is the independent variable. This is the one the researcher is in control of. It's the thing they change or select on purpose to see what kind of effect it has. You can think of it like a lever they're pulling in an experiment just to see what happens. And if the independent variable is the cause, well, the dependent variable is the effect. This is the thing the researcher is watching like a hawk. They're measuring it super carefully to see if it changes when they pull that lever. Makes sense, right? Its value literally depends on what happens with the independent variable. Okay, now this next part is, I think, one of the most brilliant twists in the entire scientific method. To really test an idea, a good researcher doesn't actually try to prove they're right. No, just the opposite. They try to prove they're wrong. They basically become a devil's advocate for their own big idea. So how does that work? Well, you set up two competing ideas. You have your alternative hypothesis. That's your original educated guess, the idea that, yep, there is a difference or a relationship, like the cost of travel by coach and train is different. But then you have the null hypothesis. This is the skeptic's position. It's the default assumption that there's no difference, nothing to see here. For example, the cost of travel by coach and train is the same. And the whole goal of the research is to gather enough evidence to be able to say, sorry, Mr. Skeptic, but we have to reject your null hypothesis. And this brings us to an absolutely crucial point. Science doesn't really prove a hypothesis is true. Let's say your study doesn't find a significant result. That doesn't automatically mean the null hypothesis is correct. All it means is that your study didn't find enough evidence to reject it. It's a really subtle difference, but it's vital for understanding how science actually works. Okay, so we've got our hypothesis, and we've set up its skeptical twin, the null hypothesis. Now it's time for the main event. We're going to bring in the data and basically put that null hypothesis on trial. So how much evidence do you actually need to reject that null hypothesis? Well, in a lot of scientific fields, the gold standard is 95% confidence. What does that mean? It means there's only a 5% chance, or even less, that the result you're seeing happened just by random luck. And if you can cross that 95% threshold, you get to call your finding statistically significant. That's a big deal. And this whole process, this trial, it pretty much follows four key steps. First, you state your two hypotheses, the alternative and the null. Step 2, you go out and collect your data from a good representative sample. Step 3, you run the numbers. You perform statistical tests on that data, and what those tests do is tell you the probability that your results are just a fluke. And then for the final step, you look at that probability. If it's less than 5%, you make the call. You've got enough evidence to reject the null hypothesis. But hold on. Getting a statistically significant result isn't the end of the game. It's not the finish line. The final and super important part of the playbook is all about quality control. A researcher has to go back and double-check their work to make sure their conclusions aren't just interesting, but that they're actually trustworthy and meaningful. This is where we get into something called validity, and it basically rests on 4 big pillars. First is construct validity. This is asking, are we really measuring the thing we think we're measuring? Like, does that test truly measure creativity or just how fast someone can draw? Then there's internal validity. This is all about asking, was it really our independent variable that caused the change? You know, did the new teaching method improve scores, or was it just a fluke because that class had a bunch of geniuses? Then you've got statistical validity. Is the math solid? And finally, external validity. This one's huge. It asks, can we generalize these findings? Do they apply to other people in other places? Or did this just work in our one little lab on a Tuesday? So why does all this validity stuff matter so much? Well, it's pretty simple, really. It's the difference between a flimsy, shaky claim and a solid finding that you can actually build on. Validity is what makes science robust, is what makes it reliable. It's what lets other scientists trust your work and use it as a foundation for the next big discovery. And there you have it. That's the whole journey. You start with that one simple, educated guess. You challenge it by playing devil's advocate. Then you test it with data, and you rigorously validate the result. That right there is the heart of the researcher's playbook. You know, this structured way of thinking, it's not just for scientists in white lab coats. It's an incredibly powerful tool for anyone who wants to understand the world a little more clearly. It helps you cut through all the noise out there and look at claims with a truly critical eye. So, now that you know the playbook, what will you investigate?